For our next part of fluid dynamics, I want to talk about Bernoulli's equation. The idea behind Bernoulli's equation is this: fluids, being made of matter, obey all of the laws of physics that we learned about in Physics 109. So things like F equals ma. If we exert a force on a fluid, it is going to accelerate. Conservation of momentum. If the fluid has velocity and changes its direction, it must have had a force exerted on it, and therefore it exerted a force on whatever it pushed on it. These are important in other classes. Bernoulli's equation comes from another thing we learned about in Physics 109, conservation of energy. So the idea is that if energy is conserved in a mechanical system, we can use that in Physics 109 to find the velocity of the ball after we throw it, assuming that it loses potential energy and gains kinetic energy. We can do the same thing with fluids. So for objects in general, we have energy in a few different forms, right? We have a kinetic energy equal to 1/2 mv squared. We have a gravitational potential energy equal to mgy. And the total energy of our object or objects is the sum of the kinetic energy and the potential energy. There's one other piece of energy from Physics 109, and that was work. So we can also have objects get pushed on by forces, and that can change the amount of energy they have. We're going to talk about the energy of fluids here in a second. So the way that a fluid can have kinetic and potential energy is still with these equations, but now our masses are density times some volume, right? So if we're talking about some volume of fluid moving at some velocity, the kinetic energy is 1/2 rho times v the volume, which is the mass, times v squared. For the potential energy, we have the same thing. Our mass there is also rho times the volume of that fluid. So we can rewrite these 1/2 rho v squared. We won't have two v's in the equation very often, so don't worry too much about that. And our potential energy is equal to rho v gy. Now, doing work on these objects is doing work on fluids is exerting a force on those fluids, and we've already seen that fluids feel and exert forces via pressure. I am just going to assert that P times volume, so the pressure times the volume, is like the ability of our fluid to do work. So this is like some other kind of energy a fluid can have. If it's at some pressure, it could hypothetically push on some object and do some work on it, and that would cost it some energy, but that energy is there somehow. So the total energy of our fluid is going to be these added together. That is 1/2 rho v squared plus rho v gy plus p times v. For Bernoulli's equation, and for fluids in general, it is very convenient to talk about the energy density, that is the energy per volume. So if we divide this total energy by volume, we see that there is a capital V in every one of these equations, so those end up canceling out. We have 1/2 rho v squared plus rho gy plus p. That is our energy density. Bernoulli's equation is the statement that if our fluid has this energy density and our fluid flows from point A to point B, conservation of energy says that the amount that the value of this energy density cannot change as our fluid flows if we're going to have energy be conserved. If our fluid flows from point A to point B, the initial energy density at point A equals the energy density at point B. We can write that like this. This is about the longest equation we've had in any physics class that I've taught, but really all it's saying is energy at point A equals energy at point B, and these energies are a familiar form, right? We have a kinetic energy density, we have a gravitational potential energy density, and we have a pressure. We could also write this as something like the first half of this equation is a constant. Sometimes you see it written like that. 1/2 rho v squared plus rho gy plus p is a constant, but I like this thinking about what's changing between 2 points, between points A and B. I'm going to erase this. While I'm erasing this, I'll say very often we don't have to use all 6 terms in this equation. Very often there are terms that are 0, or there are 2 terms, one on each side, that are the same, and so they cancel out. So it's rare to have to use all 6 pieces of that equation. Usually you're using only 3 or maybe 4 pieces of that. Let's do one example. This is a classic Bernoulli's equation example. Let's say we have a container filled with water, and maybe this is a big jug or a big tank or something like that, and there's a hole in the tank where water can flow out. So if this was, in real life, we'd see this water stream maybe, following some parabolic path as it streamed out of the container. We're not going to worry about the path it takes. We're just going to worry about what its velocity is right as it comes out of the hole. So we would like to find this velocity if we know the height h of the water level above this hole. It turns out the water level down here, or the distance between the hole and the bottom of the container, is not going to matter, so I'm not going to label it on this picture. Okay, so if we want to figure out what this is with Bernoulli's equation, the first thing we always have to do is pick what is point A and what is point B. Here are some hints for this. One of the points should be where the thing we are trying to find is. So one of the points should be where this velocity is. The other point should be where we know the most. And I claim that we know a lot at this point because we know the height of the water at that point. And we're assuming this is water. This would work for, what we're about to do would work for any liquid, and we're not going to plug in any numbers, so we'll just call this rho of whatever fluid this is. So let's use Bernoulli's equation. Before we actually write it down, there are a couple things that we can say. So if this is point A and this is point B, we have 3 pieces. We have velocity, we have height, and we have pressure. So at point A, we do know what the velocity is, or at least we can say to very good approximation that the velocity is 0. So if we imagine water coming out of this hole down here, the water level is going to go down a little bit. The water at the top is going to move down very slowly, but it's going to be much, much, much more slowly than this velocity. So we can say that the velocity there is equal to 0. We also know that at point B, we can say that the height is equal to 0, right? We'll just call this height y equals 0, and this is our y-axis going up from there. So we know one other piece. And lastly, we also know something about the pressure at A and B. So at point A, if this is, air up here and this is the water, the pressure at point A at the surface, as we saw from hydrostatics, is just the air pressure. So the pressure at A equals the pressure of the air. At point B, and this is a new fact that you should pay attention to. At point B, we are talking about the fluid flow after it has moved out of the hole. So I'm going to erase this and redraw it just for clarity here. If we were looking at a point just inside, we would not know what the pressure is, but I will tell you at this point, our water is not done being pushed out of the hole by the pressure over here. So we don't know what that pressure is. We only know what the pressure is right after it comes out on the other side of the hole, once this fluid in here is done pushing on it. So once the fluid has come out of the hole, and we're talking about, small changes in position here, at this point, when it's out of the hole, the pressure here is also equal to the pressure of the air. So once we get out the hole, the only thing pushing on us is the air, and we know what that pressure is. So what that means is PA is equal to PB. Now we're ready to plug the pieces into our equation. I'm not going to write all of the pieces. I'm going to skip VA. So we have rho G YA plus PA equals 1/2 rho VB squared. And I'm going to skip rho GYB because we know that this height is 0 plus PB. I just said that PA was equal to PB, so I can subtract that from both sides, and those terms go away. And I want to know what this VB is, so I can solve this equation for that. Also note that my fluid has the same density before and after, so my densities also cancel out. Gy equals 1/2 V squared. So solving for VB, I get 2 times G times Y, which is actually H, as we've called it in this picture. So our velocity at point B is the square root of 2GH. Students who were paying attention in Physics 109 will remember that this is the same velocity we get if we drop an object from height h above the ground. This is the velocity when it hits the ground, which means that the velocity of the fluid going sideways out of this hole is the same as if we had taken a ball here and dropped it to that height. Of course, the velocity would be downward, but the speed is the same. And that is exactly because this Bernoulli's equation is coming from conservation of energy. So if energy is conserved going from A to B, we're going to get, we shouldn't be surprised that we get the same answer for the velocity because of that conservation of energy. Let's do one more Bernoulli's equation example. We'll do one with numbers now also. Let's say that I'm looking at some plumbing, and I'm looking at some water coming out of a water main. So that is a really big pipe, carrying water to the city. And let's say we have a pipe that comes off of the water main and goes up into some apartment building or something, and then it goes to a tap where we can fill up our water bottles or whatever. Okay, so in the water main, let's say that our velocity is really small, not 0, but small enough that we're not going to worry about it. And let's also say that the gauge pressure of the water main is equal to 300 kilopascals. Let's also say that from the water main to where our water comes out of the tap, this is 20 meters of height difference. So this is a, 5-story building or something like that. All right, we're almost to what the actual question is. Finally, let's say that the area of this tap is 1 centimeter by 1 centimeter, so it's a little hole, you know, that big. What is our flow rate Q of the fluid coming out of the tap? So, I guess we can draw our little fluid coming out there into our cup or whatever. Okay, so we can write down Bernoulli's equation. We know, well, we'll call this point A when we're in the water main. We'll call this point just as we're exiting the tap, point B. This A is area, not labeling point A. I guess we'll just get rid of the glass and just put a big B there. That works well. So at point A, our velocity is small and our height is 0, right? So we can say VA equals 0, YA equals 0, which means the only thing we're left with on this left side is the pressure. Over here, we have some pressure at point B. We have the height at point B, and we have the velocity at point B. I started using Bernoulli's equation without explaining exactly why I wanted to do that. So if we want to find Q, we know from the last video that Q equals VA. So if we're given A and we want Q, we need to find what the velocity is coming out of there. So that is why I jumped to using Bernoulli's equation. What we really want to do is find out what the velocity at point B is. That's going to be enough to let us get this answer. All right, so we want VB, we know PA. PB, we do not know exactly, but we know enough to be useful here. So once our fluid has exited the tap, I'll draw a little blown up version of this. Once our fluid has exited the tap, its pressure there is just equal to the air pressure. Remember that if this is the gauge pressure, if the gauge pressure here is 300 kilopascals, then the real pressure at A is equal to 300 kilopascals plus the air pressure. What that means in this equation is PA is equal to 300 plus the air pressure, and that is equal to PB, which is just the air pressure, plus this other stuff on the right, which I'm going to write in a second. But these pressures are going to cancel. That means we also could have just used the gauge pressure for both PA and PB. That's also fine. You can use both of these as gauge pressures as long as you are careful to do that on both sides of the equation. It's easier to just always use the total pressure if you want to be consistent, I guess. So rho gy, we know YB is 20 meters, and we know 1/2 in rho, and we want to find VB. So we have 300,000 is equal to rho, which is 1,000 if this is, again, water, times G times YB, 20 meters, plus 1/2 rho, 1,000 still, VB squared. This is easy to solve. This term here was equal to 196,000 pascals. So this minus that is 104,000 pascals equals 1/2 times 1,000 times V squared. This gives us a value for the velocity at point B equal to 14 meters per second, which is like 30 miles an hour. That's pretty fast. And then plugging this into our Q equals VA equation, Q equals 14 times our area in cubic meters. So that is 0.01 meters times 0.01 meters. And that is going to give us a Q of 1.4 times 10 to the minus 3 cubic meters per second, which translated into more understandable units is 1.4 liters per second. So either one of these are good answers. This is a little easier to visualize in your head. 1.4 liters per second is a lot of fluid. So that's, filling a 1 liter water bottle in, 2/3 of a second or something like that. That is a lot of water to come out of such a small opening. Part of that could be that in a real system, the water main pressure, I looked up some average value for water main pressure. That could be reduced when the water goes into the building by some, they have devices that reduce the pressure when you go from big city pipes to small house pipes. So that could be responsible for part of this difference. The other could be all of this assumed that we're not losing any energy. And in fact, water has viscosity. It has this friction-like force that is going to cause it to lose some energy. So losing some of that energy as it goes from the water main out the pipe might also, reduce this velocity significantly and give us a lower flow rate. But this is the answer under the assumptions that we're going to make for fluid flow in this class.